So today I'll be talking about some work that I've been doing for quite a while now, which is distributed deep learning with second order methods. I'll cover some topics, but try to keep it brief. So first of all, second order methods are increasing in popularity. For example, the papers just submitted to ICLR 2021 are available on Open Review. If you take a look at the list, a lot of them talk about second order optimization and sharpness, which is equivalent to looking at the Hessian. So these methods, are very expensive and are a perfect topic to cover in a H.F.C context. And so today I'll be talking from both the H.F.C side and also more on the mathematical side. Okay, so here is my attempt to give the most mathematically simple explanation of the techniques that we are using. So I'm keeping things at a minimum. I'm intentionally not using vector notation to sort of decouple the linear algebra side of things from the calculus. And so here, you might as well view everything written, all these variables, as a scalar value, because the functions and their derivatives are the only thing that I'm trying to describe here. And later on, I'll introduce the shape and sizes of these variables and gradually introduce the complicated concepts. So first, let's consider a two-layer fully connected neural network. And there are two things that are important in this slide. The blue thing, that's called the label, and the green one, that's called the output. The output is basically the output from the neural network. So after you go through these layers, and finally go through the softmax, and then the P is output, which should be modeling the label, which is a one-hot vector with a 1 on the true ground truth label. And so you want to get this as close to the one-hot vector, but it never completely matches. So the difference between these two things is very important in today's talk. So if we use negative log likelihood as the loss function, first we define this thing called LCD, which is the loss per class per data sample. And then to actually calculate the loss per data sample, we need to sum over, well, actually, this is a cross entropy function. So when you actually multiply by the true distribution, T, or the one-hot vector of labels, and multiply by the minus log P, then you get the loss per data sample. In this case, it's 0.9. So it looks at one of these things, thinks it's a labradoodle at 0.9% confidence. And then you need to actually average over the samples. So you have this sum over the data. So these two things, sum over the classes and sum over the data, these two concepts are also very important in today's talk. So with this, you can describe the overall loss, which is summed over all the data, and then the corresponding gradient. So this is, when you say gradient descent in training neural networks, this is what the gradient is. So it's the average over the data. And now, when you talk about second order methods, so there are different variants. The first one you'd think of is Newton's method, which uses the Hessian. Also, you can use covariance matrices, which is done in the technique that we use called KFAC. Also, a more popular method in the theoretical machine learning community is something called the natural gradient descent, which uses the Fisher matrix. And I know it's confusing to have 3 different matrices, all being used as preconditioners for a second order method. Well, actually, you shouldn't actually call these second order methods, because the only thing that's a second order derivative is the Hessian. The others are actually the covariance of the gradients, and also the sum over classes for those covariance of gradients. And so, but anyway, the equivalence of the Hessian and Fisher will be shown later. So it's not a it's not a mistake to call the Fisher a second order method, because it's equivalent to using the Hessian. A nice article that describes the differences and the actual meanings of these different matrices is this article here. So if you're curious about the difference of these methods and what they actually are, then you can look at this paper. Okay, so now moving on to the actual forward propagation and backward propagation that happens. So now, with this clear definition of the negative log likelihood and the loss per data sample and the overall loss, we can define each of these things now. So first, the loss per data sample is what is back propagated. And during the back propagation, you basically use the chain rule for partial differentiation of these variables. So LD is not immediately a function of W. So you need to first take the derivative with respect to U1. U1 is the final output shown here, which is fed into this softmax function. And before that is the linear layer, which is what multiplies W1 and H1. So this yellow part is back propagated this way. To get to the first layer, you need to go through this partial derivative. But if you just want the gradients in the second layer, then you can immediately take this partial derivative and chain it with the LD derivative with respect to U1. And then this path, so each of these chains sort of diverge out whenever you cover a different, whenever you compute the gradients with respect to a certain layer. And there's this sort of spine back propagation that propagates through the inputs of all the layers and not the parameters. So anyway, if you describe the back propagation this way, it's actually doing a matrix vector product, where the matrix is the Jacobian of U1 with respect to the derivative of W0. And so you can view this as a matrix vector multiplication. In terms of the sizes, so now here, with this clear picture of the back propagation, I can start introducing the shapes of these matrices. So LD is a scalar value, 0.9 in this case. And then U1 has the length of the number of classes. So this is a 1 times number of class vector. And then this gets multiplied to something with the width of the number of classes times, in this direction, the number of the nodes in the next layer. And in this direction, the number of parameters in the final layer. And you see that these squares are sort of being stacked onto each other in like this 3D picture. In the depth direction, we have different data, basically. And you're basically back propagating this Jacobian-Vector product for each of the data samples. And then once you get these gradients, then you can sum over the data samples. And so that's what back propagation is actually doing. It's doing a Jacobian-Vector product. And this is an important thing to keep in mind when you go through the following slides. Okay, the next one is the Jacobian-Matrix product. So if you're not sure what these things are, you need to look at this chain rule here. So the gradient of the first layer per data sample can be written like this. This follows immediately from the slide I was showing earlier. The next one is showing the second derivative, the Hessian of the first layer per data sample. Now, this can easily be computed analytically by just taking another W0 derivative of this whole thing, and you get these four terms. And so the first one, you need to take the derivative of the first thing here, and this turns into a second derivative. And then the next one, you don't take the derivative of this one, but you do for this one. And then this first term, well, not term, but this first part becomes squared. And then the same thing happens, and the second derivatives appear in like later parts of the chain. And when you go to the fourth term, it appears in this final layer. And it turns out, if you really think about what these second derivatives look like, this u is a linear function of w, which means if you differentiate twice, it goes to 0. Also, this activation function, if you're using something like the rectified linear unit, it's piecewise linear. It sort of bends here and then goes straight. So if you take second order derivatives, it goes to 0. And again, all these linear layers and linear activation functions keep going to 0. And so really the final thing that you actually need to take the derivative, second order derivative is the softmax function here. Well, actually it's a combination of the log, and the negative log, and softmax. So that function, the second order derivative does not disappear. So you end up having just this term. And there's actually a mathematical name for approximating everything here, even if it's, let's consider a case where we don't have linear activation functions and these things didn't disappear. We can still approximate this thing. It's called the Gauss-Newton approximation, where we approximate the true Hessian with just this term. You can actually move these squared things to both sides. So here I'm sort of abusing the fact that these things all look like scalars. And actually, if these things were all matrices, you'd have to actually have a transpose here and then multiply the non-transpose version from the right side like this. So it has a symmetric shape, but anyway, it has this u1 derivative with respect to w0 squared. Since it's being multiplied from both sides, it's squared, times the second order derivative of the loss function with respect to u1, which is the pre-softmax, if you may. And so one interesting technique that you can use if you want to compute the Hessian is you can actually factorize this. You do compute this Hessian, but just for the final layer. And this doesn't take too much time to compute. It's only a number of classes by number of classes size matrix. And then you can actually factorize this. Okay, this square root is, again, a bit strange notation, but think of it as something that can be multiplied together. Well, it's transpose being multiplied to itself, turning into the original thing. And so it's sort of like a square root version of the matrix. But it's typically something you calculate with something like Cholesky factorization. And you use these Cholesky factors to create something that is symmetric in shape. And it's just a transpose of itself being multiplied. So you don't need to compute these both sides. Okay, so what you can do is you can compute this and factorize it, do a Cholesky, and then multiply it to the Jacobian in the same way that you do backprop. So backprop, like I said, is a Jacobian-Vector product with respect to, let's go back one slide, this gradient at the final layer. And now we're looking at a factored Hessian, one side of the factored Hessian at the final layer. So this is actually a matrix that has dimensions of the number of classes. It's a square matrix with the dimensions of the number of classes. So it's a Jacobian-Matrix product that looks like this. And once you can compute this, you can actually multiply it by its transpose to get the actual Hessian. Okay, so you can reuse whatever you computed here and just multiply the matrix to it. What you actually do in practice is you do almost something identical to the Jacobian-Vector product in backprop, but with some width instead of a vector. Okay, so this is how you can compute an actual Hessian. There are faster ways to do this I'll describe later, but this is one way to do it. Okay, and then here I'm going to describe how the Hessian and Fisher, they originally look very different, right? This one is a second order derivative, whereas this one was like the covariance being added for all of the classes. But where should I start? Okay, so these things are the same definitions as I showed in like 3 slides back. And this is the Gauss-Newton approximation of the Hessian, or if you have all linear activations, this is actually equal to the Hessian. So this is not an approximation for most practical neural networks, deep neural networks that people use. If everyone's using ReLU, this is actually equal to the Hessian. And you can rewrite this. So this second order derivative at the final layer can be rewritten because LD has this kind of definition here, right? You take the one hot vector, multiply it. So basically what you're doing is just extracting the labeled class loss. And once you get that, you can compute the Hessian of that layer. And that's what this is actually doing. Now, if you look at the Fisher and do the same kind of chain rule for the Jacobians before it, and just extract the final layer part. So first you take the derivative with respect to U1 in the same way that you're doing here. But here it's just a first order derivative. So you take that here, and then you have the same U1 derivative with respect to the weights. And then this is symmetric. So you have one here that's transposed, and you have one here that's not transposed. And you end up having these things that are at the beginning of the chain rule. Okay, so now what we need to prove is the equivalence of this green part, right? Everything else is identical between the Hessian and Fisher at this point. And we've somehow, by using this original definition of LD, we've somehow turned this into a similar summation over the classes for the given class that we are looking at. So this one hot vector represents the class we are looking at, and the LCD comes from the loss of that particular class. And you're just basically calculating backprop for that class. So here, if you further decompose this using the chain rule, so L originally is a function of P, and P is, it's not shown here, but it's a softmax function of U. So you can further decompose it into these components. Again, we're sort of symmetrically decomposing this. So the Hessian of, with respect to P, is now extracted in this way, right? So the green parts are still identical. It's just the blue part now that we need to somehow prove that's equivalent. And that turns out to be fairly easy, because if you think about the negative log function, then its first derivative is minus 1 over p, and its second derivative is p squared, 1 over p squared. And if you square this, like you're doing here, this is basically the equivalent of a matrix squaring. And So if you square this, you see that it's equivalent to the second derivative. So this is the proof. Okay. So with this, you can actually show that this Fisher matrix, Fisher information matrix, that has a lot of usage in statistics is now related to the Hessian that has a lot of meaning in geometry, right? So curvature is now related to this Fisher information. And so with this equivalence being proven for this negative log likelihood and the combination of the linear activation functions, which allows us to do an exact conversion from Hessian to Gauss-Newton, then this allows us to use these methods equivalently. And when you compute this, we actually show that they are equivalent. So here, Hessian is the red, the exact Fisher is F, is yellow, and you can further approximate these things with, without looping through all the classes, but picking up the most significant one by sampling. And also just simply taking the covariance of the gradient. So these are all different things. And you see that the blue one is very different. But if you compare the red against the yellow, then you see that the red and yellow lines are almost on top of each other. So we do further approximation of these matrices. The full one is the star without approximation. The circles are block diagonal approximation. The black triangles are Kronecker factored approximation, and X's are diagonal approximation. So diagonal approximation is very crude. It doesn't really work. Kronecker factorization is somewhat close to the circles if you compare the circles and the triangles. And the circles and the stars are somewhat close. But the point I want to make here is the equivalence between H and F. You see them almost on top of each other. What we're looking at here are the top 10 eigenvalues. So you can see that the eigenvalues drop quite rapidly for all of these matrices, but we are able to compute them efficiently using either the Hessian or the Fisher, or this sampling technique, which is even faster than computing the Fisher, and the covariance, which is the fastest, but not very accurate. So when we were initially doing the work with KFAC, we were using this covariance. So this is a more recent study looking back at what we were actually using as a preconditioner and sort of looking at its properties. In hindsight, it wasn't the best preconditioner, but it was very cheap. So now I'm going to describe a little bit about the computational cost. And maybe this is all a trade-off, right? If you can get similar results very cheap, then you might sacrifice accuracy sometimes. So by accuracy, I'm talking about the accuracy at which you precondition, not the final accuracy that you get during the training. Okay, so we looked at Jacobian-Matrix products, which actually backprops a matrix instead of this vector here. The pros for doing this are that you can actually obtain the actual matrix. This is different from the Hessian vector product, where you can only obtain the Hessian vector product itself. You can't extract the H from it. So if you want to manipulate the H or store it or do something like factorize it and use it afterwards, if there's any kind of usage for the matrix itself, then Hessian vector product is actually not sufficient. So the good thing about the Jacobian matrix product is that you can actually obtain the matrix itself. However, since you're backpropping a matrix that has, where this one turns into the number of classes, you have that much more memory consumption during the backprop. And because the autograd inside TensorFlow and PyTorch do not actually support this kind of Jacobian matrix product, you need to write custom functions to do this matrix product. And so you can't rely on existing software to do this. So every time you bring a different module into your model, you need to write something, which is a pain. On the other hand, the Hessian vector product also just uses the autograd in place, right? It's just using the Jacobian-Vector product and slightly modifying it so that it can compute Hessian or Fisher vector products. In this case, if you want the equivalent thing, then you will need to loop over the number of classes, because you are, in the end, computing the same thing. Then you either backprop, the number of classes worth of vectors, or you backprop that big thing at once. That's basically the difference. Okay, and this is a very interesting problem to look at from a computational point of view. So what are the costs? What's the trade-off? How much communication does this require when you look at this from a distributed point of view? And how much memory can you actually save by throwing away these components, doing some parts matrix-free, for example? So what are the trade-offs? This is an interesting question that I'm not going to describe in too much detail in today's talk. I'm just describing that there is this contrast between these two approaches in the popular ways to compute second-order matrices at the moment. Okay, one more thing that I'll describe briefly before I move into some of the results is the Kronecker factorization. So I've mentioned in many of my talks about Kronecker factored approximate curvature, KFAC. We've done a lot of work training various computer vision models with this type of approximate second order method. Here I want to describe where that Kronecker factor actually comes from. So if you remember this backprop chain rule, when you look at this particular layer between this red and blue part, so this is the first layer in the network, the product between this and the product of these three things, which is shown in blue here. So the product between these two red and blue parts is actually what turns into a Kronecker product. And the reason is very simple. So if you look at, for example, this second layer, and you look at this derivative, U1 and W1, it forms a Jacobian matrix that looks like this, okay? And then if you think about this linear relation, then I'm sort of abusing notation. So here I'm describing W1 as the component, first element of this derivative, whereas this W1 describes the matrix, entire matrix here. So this entire matrix is called W1, but I'm sort of abusing the notation here. But if you think about all the Jacobian elements, only the ones where the indices match are actually valid. So you have this sort of diagonal matrix, which has the entries of H, and the other parts don't have entries. And then when you multiply that with this gradient, it actually turns into like vector multiplication, like a BLAS1 thing, right? Which is essentially, it looks like a scalar times, vector outer product. That's what it turns into. So if you view vector outer product, a vector times vector that turns into a matrix as a Kronecker product, which is what it is, then you can easily understand that this is a Kronecker factor. So when you say Kronecker factored approximation, it's not the Kronecker factorization of this this Fisher matrix that is an approximation. It's the swapping of the order at which we multiply and then take the summation that is the approximation. Usually you have to do the product and then do the averaging, whereas we do the averaging first, during the approximation and then take the product. And of course, you can't swap addition and multiplication. So that's where the approximation is coming from. Okay, so with that described, we can start looking at, for example, the costs of the backprops. So basically, this one is computing the matrix vector where it says x times v. And these are computing the actual matrices themselves, but with the Kronecker factorization and diagonalization. And this f, the cost is huge because it has to loop over the number of classes, right? So it has a lot of backprops, and that's why it's expensive. Whereas the other ones, so this red one, as Amir described in his talk a week ago, you can actually do a Hessian vector product with 2 backprops. And also one backprop plus a backprop of this thing here is what is computed here. And these are much cheaper still than the Fisher matrix. But so the important thing here is that these are Hessian vector products. You can't actually obtain the Hessian this quickly if you want the actual Hessian. So that's one thing to keep in mind. Okay, so now a little bit about the distributed side of things. So we've tested that block diagonalization and Kronecker factorization are fairly accurate. And we actually did the training and saw that it does not introduce significant error when validated against a full matrix. So what we can do then is we can do a block diagonalization of the matrix per layer. So each block represents one layer. We sort of decouple all the layers and compute their Fisher matrix. And then we can do something interesting if we can do that kind of block diagonalization. We can actually reduce over the data and then scatter the matrix blocks for each layer, right? So this reduce scatter is actually switching from data parallelism by reducing the data that's distributed. And then we're now switching to sort of a form of model parallelism. It's not actually model parallelism because it's not the parameters that we're distributing. It's the matrix blocks that we're distributing because that's the expensive part in our method. But because we can scatter that part and process that in a distributed fashion. So basically we can do the factorization and the preconditioning using these matrices with each GPU handling one layer. So even if you had 100 layers, if you use 100 GPUs, then basically it's the same amount of computation as one layer per GPU. And so you can reduce it that much and also combine that with Kronecker factorization, which reduces the complexity by a square root of the original complexity. Then you can compute these things quite fast. And so a lot of the second order methods actually don't try to compare with first order method, like the state of the art first order methods. But what we did was try to compare against the most challenging first order example, which is this ImageNet training where SGD is like optimized like crazy. And so the baseline here is like very, very optimized, very tuned to this specific problem, so much that people have sort of started to rethink if this is a useful thing to do. But our idea is not to break the limit here like other SGD people are doing. We just wanted a very strong baseline. And so we compared our second order method in terms of the execution time with these methods. And so in the end, now the current record is like 30 seconds, I think, by Google using their latest TPU. But at the time, Google was still 2 minutes, and we were beating them at, oh, sorry, this is only showing time per training step, but we only require about 1,000 steps to converge. So basically, this millisecond turns into the second for the total runtime. So this is, if it's 108 seconds for the total runtime, it's faster than 120, 2 minutes. So Our goal is not to claim, that K-Fac is superior as an optimizer. We just wanted, to do apples and apples comparison in terms of the data set and the problem and the accuracy that we're achieving, things like this. So some people were, sort of complaining that we were only going to 75%. So we actually trained until 76. And also, okay, so again, clarifying what we are trying to prove here. So the sole purpose of doing these experiments is, to prove that we can do these second order, compute these second order information fast and accurately, right? Where we have something that's matching in terms of the top eigenvalues, while we can compute this thing fairly cheap. And so we are providing like a point of reference for, like a reference of comparison for people who are doing various approximations of these matrices. If they want like the exact version to compare with, we can provide that. So once we can get these things to work, there are various applications that we can look at for the Hessian, Fisher, and covariance. So a lot of these gradient-based hyperparameter optimizations always have these Hessians in them. Bayesian inference requires the Fisher matrix. A lot of people just do diagonal approximation of it. And also preconditioning optimizers, which is what we were doing originally, we can now do with various types of preconditioners, not just the covariance. Now we can do it with more accurate versions. And also there are things like generalization metrics to sort of be able to predict how much your method, your model will generalize without actually doing validation on it by looking at these metrics. And if you can have these metrics, you can actually regularize with them and to achieve better generalization, to find models that achieve better generalization. So in any of these, you still have things like the Hessian and covariance. For example, the reason why Hessian vector products are not sufficient can be seen here. If you can only do a Hessian vector product, you can't compute this thing because this is not a Hessian vector product. This is, you need the explicit Hessian and then invert it, or at least factorize it, and then multiply that to another matrix. So that's the reason why you need these alternative methods. Okay, so in summary, I've described that these things have many applications beyond preconditioning that we were originally doing. It's not just an optimizer that we're trying to find. Also, diagonal approximation of these matrices is often used without justification. Many studies just suddenly diagonalize the matrix for a reason that's coming from computational limitations and not because of justification from an accuracy point. Also, comparison against the full matrix is now possible for smaller data sets. It takes time to do this for larger data sets and models, but it's definitely feasible for smaller data sets. So we can validate them there. We can validate these Kronecker factorizations or approximate methods there with smaller methods. And then once we've validated them or found the reason why, if they're inaccurate, why they are inaccurate, then we can fix them. Once they're fixed, we can use them as optimizers with minimum overhead. Also, this overhead of computing these matrices decreases proportional to the number of processes. And this is an important thing. If you're doing things in a highly distributed manner already, if you're doing SGD in distributed, then the overhead of adding these second order preconditioners is smaller and smaller if you're the larger that you're training with. The more GPUs that you're using, the less overhead that you can expect. If you're only using one GPU, second order methods are very expensive. But if you're doing distributed, it's not very expensive. That's what we were able to prove. Also, with these tools, we can perform various comparisons that I've showed just one example in today's talk, and which can be used to validate theoretical work where a lot of these Hessians and Fisher matrices appear. Okay, so that I think I went a little bit over time. Thank you for listening to my talk.
Okay, Thank you, Rio. No, you were not over time. So once again, thank you for the lovely talk. And thank you everyone for attending. We'll take questions in just a moment, but I do want to mention that we will be having another SPCL BCAS talk in 2 weeks on October 22nd. Please check our website for more details.